Hi and welcome to a new chapter in machine dynamics. This chapter is, I would say, the largest chapter of machine dynamics of this course, and it covers the Jeffcott rotor. So basically bending vibrations of a rotor, as you can see, that is designed by a shaft and a disc. And what we are studying are the bending vibrations of this shaft or of this rotor dynamic systems. And there are 5 videos on this subject. The first video, so this one, will deal with the classical Jeffcott rotor, so with the model that you can see here. After that, there are 3 more videos, and these 3 videos cover special effects, I would say additional effects that are introduced into this very simple model of the classical Jeffcott rotor. So in order to make it a little bit more complicated, one could say, but also a little bit more adapted to reality, of course, and studies the influence of these additional effects. And then there is a last video that covers multi-disc rotors, so moving from one disc to several discs, until, I would say, until infinity, one could say, so until the continuum rotor, which is just the shaft, so without any disc or with infinitely many discs, modeled as a continuum, so as a bending beam. Well, as I said that in the last video, we will treat that shaft as a bending beam. Here in this video, in the first one, it seems to be not a bending beam, or what? Well, of course it's bending, otherwise we couldn't study bending vibrations, but there is something special with that model here. Namely, we will somehow separate the mechanical properties that we need in order to describe a vibrating system. What are these properties? Well, we have the mass properties or inertia properties, we have the stiffness and the damping properties. So stiffness and the damping properties, I would say, on one hand, as they provide the restoring forces, and on the other hand, we have the inertia effects. And they are assigned to different objects in that model. Namely, the inertia properties are assigned to the disc. The disc is assumed to be a rigid body, while the shaft itself is assumed to be elastic, because we want to study the bending vibrations of that shaft, but not in the classical beam model, so with distributed mass, but as a massless elastic shaft. So basically it could be represented by a spring element. So as we also consider the damping here, it must be represented by a spring and a damper. So a spring and a dashboard damper on both ends of that shaft. So they relate, they connect the bearing, which is assumed to be rigid, with the disc. The disc carries all the mass properties, so that is mainly the mass of the disc and the mass moment of inertia for rotation. And then you can see that on the opposite end we also have a shaft which is to be assumed to be the same as the first shaft and is modeled also as a spring and a dashboard damper. So on both ends of that disc we would have then a shaft, and we can then of course also summarize these 2 springs into one element with stiffness C and damping D. So basically this would be the model. Let me summarize the assumptions again. So first we said there's a rigid disc carrying the mass properties, and then there's a massless elastic shaft carrying the restoring forces. The bearings at both ends are assumed to be rigid. Gravity for the moment is neglected. You can see in this drawing there is no gravity included, so basically you have to turn around that figure by 90 degrees in order to study this system without any gravity effect. Then for the damping here, we will assume that it's velocity proportional damping, so external damping, one could say. Finally, the disc is mounted without any inclination, so it's straight or vertical to the shaft, perpendicular to the shaft, and we're just studying bending vibrations, and we do not study any torsional vibrations. Torsional vibrations will be also studied in this course of machine dynamics, but not in this chapter, not in the next chapter, but after the next chapter we will move to torsional vibrations of drivetrains. So torsional vibrations are very important for drivetrains, but for these rotor dynamic system with one rigid disc and a very flexible shaft, usually torsional vibrations are of less importance than these bending vibrations. And finally, well, there must be some kind of torque, driving torque for this system, and we will assume that this driving torque has a linear characteristic here. So these are the assumptions, and you can see it's a long list of assumptions, and basically this is the reason why there are 3 more videos that detail special effects. Basically, we will assume that these assumptions are present here in this first video, and in the next video we will relax these assumptions one by one and study the effect of these additional assumptions separately by assuming, for example, that we have elastic bearings, or that we include the gravity, or that the shaft, which is still assumed here to be circular, will be non-circular, so without having here an isotropic stiffness, C. We will introduce internal damping, for example, and well, then, as I said, we will also consider the inclination of the disc and then move to multi-disc rotors and also to continuum models. So assuming then at the very end that the shaft has a certain mass and is modeled as a bending beam. Yeah? But for the moment, this is already enough here. Now the first step is to derive the equations of motion, and then we would learn from the solution of these equations of motion, we would learn something about the properties of this Jeffcott rotor. So if you look at the equation of motion, then what you can see is there are several points in that figure that play a certain role. First of all, let's have a look at the coordinate system that is introduced here. So where is the origin O of that coordinate system? Can you see it? It's a line, a theoretical line, that connects the center of the 2 bearings. This is the origin of the coordinate system, and this coordinate system is an inertia system. Usually the lateral axis is the y-axis, and the vertical axis points downward and is denoted by Z here. So these are the axes, and now in this inertia system we can identify 2 very important points. One is denoted by the letter W, and the other one is denoted by the letter S. So what is point W and what is point S? They will play a crucial role in the next videos. Point W is the point where the shaft connects to the disc. It's perhaps in the center, in the geometric center of the disc. S, it's the center of gravity of that disc. Keep in mind that the disc carries the mass properties, and therefore the center of gravity is of very importance of the disc. You can see that W and S do not mark the same point. There can be a difference. Basically, that means that the center of gravity is not in the geometric center, or is not coinciding with the connection point between the shaft and the disc. So there is a kind of eccentricity, there is a kind of imbalance, and we will study the influence of this imbalance in the next few slides. So this is already very important to retain. Yeah? So these are the important points. They are of importance for the derivation of the equation of motion because the restoring forces relate to point W. So in the free body diagram, we will see them at point W, while the inertia forces have to be related to point S, to the center of gravity. So they have to be marked at different points, and therefore we need W and S. So let's have a look at the free body diagram of the disk. You can see again our coordinate system. Of course, that's a little bit exaggerated. Usually that eccentricity is quite small, and also this displacement here between the origin of that coordinate system of our inertial system and the point W is much smaller, but for obvious reasons, so that you can see something, I exaggerated here a little bit. You can see that there are coordinates assigned to point W. These coordinates carry the index W, makes sense, and the same holds for point S. Of course, it's already very important to remark here that there is a kinematic relationship between the coordinates for point W and for point S. Why? Because both points sit on a rigid body. So during the motion of that rotor, the relative position of these 2 points cannot change. Otherwise, the body wouldn't be rigid but flexible. So they are sitting on a rigid body, and they can be characterized by E, so just by the distance between W and S, and then we need to measure the angle between W and S, and this can be measured by that angle that is introduced here. So can be related to an angle that will be introduced and will be later on denoted by E. Let's come now to the free body diagram here. So the free body diagram shows the restoring forces, so the spring forces in lateral and in vertical direction. They point opposite to the axis because they are restoring forces. Same holds for the damping forces with the first order derivative of the coordinates. So all these coordinates are time dependent, will change in time during the rotation of the rotor. And finally, we see in the second order derivatives, so the accelerations of the coordinates of point S for the inertia forces, and also the inertia forces point opposite to the coordinates Y and Z, to the coordinate directions Y and Z, because we consider D'Alembert forces, the forces in the sense of D'Alembert. There are some other quantities here, so keep in mind that there is also the mass moment of inertia times the angular acceleration here, and that we have the driving torque, which points in the direction of this angle phi here. So from this free body diagram, we can read, or we can write down, the balance of forces and the balance of momentum, angular momentum. Why do we need a balance of angular momentum here? Well, because we have in total 3 degrees of freedom. 2 degrees of freedom relate to the bending motion, to the bending displacement of the shaft. So basically, for example, to the coordinates y sub w and z sub w. The other 2 coordinates of the point S can be computed from kinematic relationships from these points. So these are 2 degrees of freedom. And the third degree of freedom, which is, I would say, so clear somehow that one forgets about it, is the angle phi, the angle of rotation of that rotor. So it's a rotor, so it will rotate, and therefore will have at least 1 degree of freedom. So let's write down the equations of motion from that free body diagram. So what we can read in the y direction is the balance of all the forces in y direction, taking the inertia forces in the sense of D'Alembert, leads to negative terms for the spring force, negative term for the restoring force of the damper element, and negative term for the inertia force. Same in z direction. And now the last equation will be related to the balance of angular momentum. So you will find J and the mass moment of inertia and the angular acceleration with a negative sign here. Look at the direction of that angle phi. It marks the positive direction. The driving torque is of course positive. And then we have contributions coming from the restoring forces, the spring restoring forces and the dashboard damper forces, which are multiplied by a lever. The lever is E cosine phi for the z direction. You can see E. And if that angle denotes angle phi, then you will find E cosine phi for the z direction, and you will find E sine phi for the y direction. And if you look at the action of these forces, then you will find that they will generate an angular momentum in or a torque in the positive sense. So will rotate clockwise for the vertical forces in that direction, for the forces in y direction. So the restoring forces here, you can see they rotate or will create a torque that rotates opposite to the phi coordinate, and therefore we have the negative sign here. So these are the equations of motion. And now the question is, are we now at the end of that video or not? No. This will be a quite lengthy video, and we have just done the first steps. First of all, what we can see is the way these equations of motion are written here is not satisfactory at all. Why? Because we have two different sets of coordinates. Sets of coordinates pointing to the point W and other coordinates that are related to point S. And at the very end, I would like to have just one set of coordinates, as there are just 3 degrees of freedom. So we have to introduce a kinematic relationship. And then the next question is, we would not want to stop here by writing just down equations of motion. We would like to understand and learn something about our system. So therefore we have to solve the equations of motion, and then the question is, can we solve these equations of motion, or are they too difficult to solve? So let's move to the kinematic relationship first, and then let's try to modify the equations of motion, and then we look at the modified equation of motion and discuss whether we are able to solve them or not. So, kinematic relationships. The kinematic relationships relate point S to point W, and as I said, you need an angle here. It's for the moment the angle phi. So the y-coordinate ys is related to the y-coordinate of point W by E cosine phi. Then you can take the derivative, first derivative, because you need, if you want to keep, for example, the coordinates in point W, then you need the acceleration of point S. So you need the second derivative of ys. The first derivative is given here. Don't forget that the angle phi depends on time t. Finally, you take the second derivative. So you have to take here the second derivative of phi, and you have to take also the derivative of that angle phi, which is the argument of the sine function. This leads then to the last term here, to E minus E phi dot squared cosine phi. We will do the same with the z coordinate. So for the z coordinate, we will find that zs is that v plus E, which is the hypotenuse, and the corresponding projection in vertical direction is given by the sine function, by multiplying E with the sine function. We also take the first and the second derivative here, leading to the velocity of that point S in vertical direction, and finally leading to the acceleration that we need in the representation of the inertia part of our equation of motion. So there we have the second derivative, and also here don't forget that the angle phi depends on time. Now we insert these equations into the equation of motion. So what do we have to change then? Well, we have to change the first two equations. In the first two equations, we had products of the mass times the acceleration of point S in lateral and in vertical direction. As you can see, what you get now is the same here for point W, so mass times the acceleration, but you get some additional terms. These additional terms do not depend on the coordinates of point W, but they depend on the angle phi, on the angular velocity, and on the angular accelerations. So I will move all these terms to the right hand side of my equation of motion, and on the left hand side I just will keep the inertia term relating now to point W. I will keep the restoring forces, so the damping term and the stiffness term. So the equations of motions, they look like follows. You will find here the acceleration term. I've changed the sign, also adapted the sign here. So therefore, on the right hand side, these two terms appear with a positive sign. So you will find the inertia term, you will find the damping term and the stiffness term. And on the right hand side, you will find something that would be related to kind of excitation for that looks like a single degree of freedom oscillator, right? For that single degree of freedom oscillator, if we interpret this as the single degree of freedom oscillator, we would have this excitation function on the right hand side. Next, we do the same in Z direction, and we move these two terms also on the right hand side, and as this one was positive here on the right hand side, on the opposite side it gets a negative sign here. And finally we have the last equation, and we also write them in a little bit better way. We take the driving torque on the right hand side, so as excitation, and all the other terms on the left hand side. So these are now the equations of motion, and now the question is, are we able to solve them? Well, if you look at these equations of motion, you will say, no, I'm not able to solve them because they are coupled. You can see that the first two equations are coupled via the excitation with the degree of freedom phi, which would be described as the last equation. You can see the second order derivative of phi in that equation. So the first two equations are coupled with the last equation via the function phi of t. And on the opposite way, the last equation is coupled to the first two equations by these two terms here, the second and the third one on the left-hand side, which relate to the displacement and the velocity of point W. So, first negative message, equations of motion are coupled. Second negative message, these equations of motion are highly nonlinear. Why? Well, look at the function phi. First of all, you have a sine function, the sine of phi, the cosine of phi, which are nonlinear function. Then you multiply phi, the acceleration at least, by sine phi, and you multiply the square, even the square of the angular velocity. So again, it's a nonlinear function by a nonlinear function in phi. And if you look at the last equation, then there are some more nonlinearities. You multiply the coordinates of y and also the velocities by sine phi, and you do here the same with cosine phi. So we have three coupled nonlinear ordinary differential equations. However, I'm still able to solve that system in a special case, namely for the case of stationary motion. So for the moment, let's assume that there is stationarity of the motion, and then I will show you that for this case a decoupling of this equation of motion is possible, and not only a decoupling of this equation of motion is possible, I'm able to solve the first two equations because they represent then linear equations for a single degree of freedom oscillator under excitation by a rotating imbalance. And from the last equation we will derive conditions for such a stationary solution to exist. So I would like to study the decoupling and the first two equations at the very beginning of the next step of that video. And after we understood that stationary solution and its properties, so relating to properties of that rotor dynamic system, of course, then I would like to answer at the very end the question whether this stationary state exists and how we can find them. So the positive message at the very end will, of course, that there are stationary states, otherwise it wouldn't be necessary to do the first step here. Okay, so let's look at the decoupling in for the stationary state. So what is a stationary state here? Stationary state means that, well, the first order derivative of angle phi, so the angular velocity, is a constant. The rotor rotates with constant rotational velocity or with constant rotational speed, or simply saying with constant speed. It rotates with constant speed, so the second derivative, the angular acceleration, will be 0. The angular velocity will be constant. The angle itself will be a linear function. So this will be the general assumption for stationary operation, and at the very end of that video we will discuss that equation or discuss whether these stationary states exist or not. Okay, if the angle phi is then a linear function of time t, it can be represented by the angular velocity times t plus an angle phi naught. And without loss of generalities, in general you can choose, you can start, if you remember that angle phi, you can start at a position where this additional constant here can be set to 0. So we will represent phi simply by omega times t. Otherwise you just have to turn a little bit your inertia system to reach that condition here. Okay, now let's look at these equations. Do they decouple? Well, we will lose that information here. The angular acceleration is 0. For the angular velocity, we assume that omega is constant and given. So the right-hand side will be a given function, including omega squared cosine omega t, omega squared sine omega t. So the right-hand side is known. We are just looking at the left-hand side and want to compute y sub w and z sub w, the coordinates of our point w, the connection point between shaft and disk. And as you can see, these are linear equations. They are decoupled and they represent single degree of freedom oscillators. So the equations for bending vibrations for these coordinates, for these bending displacements, are the equations of a single degree of freedom oscillator under harmonic excitation, so by harmonic function, and the excitation is represented by that excitation of a rotating imbalance, a rotating mass force, and they have identical left-hand side because all these parameters are the same. We do not have any difference in the damping properties represented by the vertical and the lateral direction, and we do not have in the simple model any difference in the stiffness property of the shaft related to the lateral and the vertical direction. And therefore all the parameters on the left-hand side of these two equations of motion are the same. We therefore have the same left-hand side of that of these equations to the same system properties, and these system properties are important for the representation of the solution, the particular solution that we want to compute for y and z. The only difference is the harmonic function on the right-hand side. If we move to standard parameters, or the standard form of these equations, as you have seen in the chapter before on vibration isolation, you just divide the equation by m and then you introduce the standard parameters. Then what you can see is the left-hand side, of course, looks the same in both equations. And for the right-hand side, the only difference is the choice of the harmonic function. In the first equation, it's a cosine. In the second equation, it's a sine. There's just one thing we can see from that representation. Namely, we can read directly the natural frequency, natural circular frequency of that system, namely omega k squared is equal to c divided by m. You can see that I denoted that natural frequency not by W0 or W0, but by omega naught, but by omega k. The k refers, and this is the general language here in that chapter, to the term critical. What is critical there? Well, there's another omega in that equation without a k. It's that omega from stationary operation. It's that omega that comes from the rotational velocity of the rotor. Now assume you will have omega equal to omega k. What will happen? Well, you will be in or close to resonance. And this is called the critical velocity. So omega k in that language of rotor dynamics is not called, it's of course the resonance, or for the undamped system, the resonance frequency, or it is the natural frequency, but it's often called here, it's the critical rotational velocity, or simply the critical speed. And therefore the index k here for the German word kritisch, written by a k, and not the c, index c here for the English word. Okay, so we note that there's resonance at omega k, and omega k is the critical rotational velocity for that system. It was termed critical rotational velocity for that system. Now, when we want to compute the particular solution for the displacements, then it makes sense in that setting to choose a cosine omega t plus some angle epsilon for the y component, and to choose a sine function. You can see it's written here with an alpha and a beta for the z component, for the vertical component of the coordinate. Why? Because then formally these two equations look the same. So you can see there are amplitudes y and z, but these amplitudes will be the same. These are the classical magnification factors that you have seen for that single degree of freedom oscillator that is excited by a rotating imbalance or by a mass force. And for that angle alpha and beta, they are also the same, and they are the classical phase shift, and this is now the letter epsilon I mentioned before. So y and z, these two amplitudes introduced in the particular solution for the displacement in lateral and vertical direction of the point W, are then equal to the classical magnification factor. And that magnification factor, keep in mind, it's related to a rotating imbalance. Therefore, we have E times eta squared in the numerator of the magnification factor, and then we have the classical denominator here. And also, epsilon is then alpha equal to beta. It's a classical phase shift. It's given by the arctangent of 2d eta divided by 1 minus eta squared. Okay, here I would stop in a course of engineering mechanics, in a classical course, and would say, okay, we have derived the equations of motion, we have solved the equations of motion, and that's the solution, well known to you, and that's it. But now we want to learn something. We want to learn something about our rotor dynamic system. So what can we learn here? We can try to understand the geometric interpretation of that. So what is the sense behind all these equations? Let's have a look at the geometric interpretation. So here you can see the situation. Also exaggerated, of course. We have our inertia system. You remember the origin of that coordinate system? It was the connection point between an ideal line that connects the centers of the two rigid bearings. We have our lateral coordinate, we have our vertical coordinate, and what you can see here is a position vector r sub w that relates, or that is drawn from 0, from the origin of that coordinate system to point w. You can do the same from 0 to point S. And now I would like to compute the length of that vector, r sub w, and that length of that vector is also called r sub w. The vector itself would have a vector arrow on it, same for rs. So r sub w and r sub s denote the length of these position vectors. Let's move to r sub w. Clearly r sub w is represented by the Euclidean sum, I would say, the Euclidean norm, so Pythagoras is applied here, to compute that length of r sub w. It's yw at the particular solution squared plus zw particular solution squared, and then you take the square root. And now if you look at the representations of that particular solution we took with the cosine function and the sine function here, you can directly apply the trigonometric Pythagoras, and you observe that r sub w is equal to v, and this is a constant, and v is the magnification factor. It's a constant as long, well, of course, as you do not change the system parameters, but why should you change the system parameters? It's always the same rotor. And as long as you do not change the rotational speed of your rotor, so you operate in stationary state. Then as r sub w is a constant during that motion, so that length is unchanged, point w, which moves in this inertia system, moves on a circle with a radius r sub w. And that radius is constant. So we have the circular motion. We have discovered that point w is on a circular motion around that origin of our inertia system. A circular motion in the inertia system. Okay, as r sub w depends on eta, or I could say it depends on the rotational velocity, we can ask about the asymptotics of that r sub w, of that length, of that distance between the origin and w. Asymptotics means we are asking for very, very low rotational velocities, so eta close to 0, and very, very large rotational velocities, high-speed rotors, where eta tends to infinity or becomes very, very large. Well, for this to discuss, I will plot the magnification factor. You can see it here. It's the classical result you saw in Engineering Mechanics 4. That magnification factor, keep in mind that in the numerator we have the product of E times epsilon squared. So starts at 0 for very low values of eta, so very low rotational speed if you keep the system parameters and therefore the natural frequency constant, and moves then to a value of eta in the asymptotic case, to a value of E in the asymptotic case that eta tends to infinity. Independent of the damping, if the damping is very, very small, you find a very pronounced resonance here, so therefore critical speed. So keep away with your rotational speed from this regime, from values of eta close to 1. And so asymptotically, we will find for low speed rotors a value of 0 for R sub W. That means that the connection point between shaft and disc is then very, very close to the origin, while in the case that we have a high speed rotor, R sub W, the distance between the origin and the connection point between shaft and disc, is equal to the eccentricity E. Okay, that was, I would say, quite simple. Now let's look at R sub S at the distance between the origin and the center of gravity. Well, first of all, one could guess that there must be also a circular motion, because point W is on a circle around the origin. The length between point W and point S, the center of gravity, is not allowed to change because they both lie on that disk, which is a rigid body. So then what should happen? Should be also a circle. But let's determine the length of that vector Rs. So the distance R sub S. So first of all, what we know is we know that R sub W is equal to V, and we know that tiny little length here, the distance between W and S, so E. So we have already two informations in that triangle, and we also know that angle epsilon here. It's given from the particular solution, and it's well known to you. It's the classical phase shift. We have that information. Well, with that information, we can compute the length Rs using the law of cosines. So Rs squared is then V squared, Rw squared, plus E squared, that here, minus 2 times the product of E and V, so the product of E and R sub W, cosine pi minus epsilon, so the cosine of that angle that extends from Rw to E, to that line that connects W and S. Well, there is one problem in that equation. It contains, well, can modify it, then it contains cosine of epsilon. So we have V squared plus E squared, and then we change the sign and we have plus 2 times E times V cosine epsilon. It contains the cosine of epsilon. We know the tangent of epsilon. The tangent of epsilon is related to the cosine of epsilon, or can be related by applying the classical trigonometric Pythagoras and then solving for the cosine of epsilon. Then you get 1 divided by 1 plus tangent squared of epsilon, and you take the square root of that expression. Now you can plug in the result for the tangent of epsilon here, and you get something. If you do it, you get something that in the denominator looks very familiar to V, right? So the denominator of that expression for cosine and of epsilon and the denominator of V, they are identical. That's good, because then we can introduce the magnification factor here, V. It's simply 1 minus eta squared. Then you have to divide by E and eta squared, and then you can multiply by V, right? Because both terms share the same denominator. No? Then it's just 1 minus epsilon squared E divided by E times epsilon squared V, and you arrive at this expression here by inserting V from above. So we can replace the cosine epsilon by a term that contains a certain factor, I would say, and V. So we get again here also V squared. So we have 2 terms containing V squared. That's good. So Rs squared is then V squared plus E squared plus 2 times 1 minus epsilon squared E divided by E epsilon squared V squared, and we have to multiply by E again, so we will lose that E here in the denominator. So we get 2 times 1 minus eta squared divided by eta squared, and v squared from one v that sits here, and the other v is that one here. Okay, well, then we can collect the first and the last term. Keep in mind that you divide here by eta squared, so you have minus v squared. Here you have a plus v squared, so the first and the last term will go away, and you will have e squared 2 times minus eta squared divided by eta squared. Don't forget that you have here the 2, which is multiplied with the whole ratio. Therefore, you have a minus 2 times eta squared divided by eta squared, and now you have just 1 left of that eta squared divided by eta squared. E squared plus 2 times 2 minus eta squared divided by eta squared, v squared. Okay, so what can we do with that expression? We can introduce also in the first term here v squared. So in order to separate that v squared. How is that done? Well, look at that expression for v. It contains in the numerator the e, because we are considering a mass force or a rotating imbalance. Therefore, we have the e here. If you square that result, you obtain an e squared here. Now you can solve that equation for e squared, leading to v squared multiplied with the denominator squared, so without the root here, and divided by eta squared. That's good, because here we also have the eta squared. So in total, we will find, well, in total we will find eta in 4th power, because we squared that equation, so we get eta in 4th power. We get the denominator squared, which is now in the numerator. So we are discussing the term in e squared. It's the first one, it's the second one, and then comes the term, the second term here, where we multiply the numerator and the denominator by eta squared in order to achieve a common denominator of eta in 4th power. So therefore we add plus 2 eta squared minus eta in 4th power. And we have to multiply all that expression by a v squared. Now, let's have a look at that expression again. So we see that we have 1 minus eta squared. This calls for a binomial formula, namely for 1 minus 2 times eta squared. That's good, because we have plus 2 times eta squared here. Plus eta in 4th power. That's also good, because we have minus eta in 4th power there. It's nice, right? We lose nearly all the terms in the numerator here, except for the first one, if we apply the binomial formula, 1. And the middle term, 2 d eta, which is the only term that contains the damping, by the way. And of course, in v, the damping is also hidden, but in that ratio, that's the only term where d is explicitly present. So we get just 1 plus 2 d eta squared. The eta in 4th power moves now to v, so v divided by eta squared and then squared, then we have eta in 4th power, and this is the solution we obtain here. Does that look familiar to you? You will say no. Let's study the asymptotics, and then I will be quite sure that you discover something that looks familiar to you. First, let me remark that we have to take the square root of that expression, because here we have computed rs squared and we want to compute rs. So we take the root of that expression, and then maybe it starts to look familiar to you. Let's look again at that equation. So first of all, I recall the magnification factor and the phase shift, and this was the equation we derived on the last slide after taking the square root. Do you remember something like this? The magnification factor times 1 plus 2 d eta squared. And if you take into account that that magnification factor is not the classical one for a force that acts directly on a mass, but It's the magnification factor that is modified by, in the numerator, by the term E times eta squared. The eta squared goes away, and then it's just the E we have here. This looks familiar to you. It's a classical result we obtain for vibration isolation, for active vibration isolation. It's that figure here. With that miracle, I would say, where all the curves passes through this point here. This figure is recovered if we divide, so if we relate Rs to E, if we divide Rs by E, and, well, plug in the expression for V here. And from that figure, we can immediately see the asymptotics. For eta equal to 0 now, keep in mind that you consider here the ratio Rs divided by E, and that ratio tends to 1, so Rs tends to E. And for eta to infinity, Rs tends to 0. Now, is this just a coincidence that we get the results we obtained before for active vibration isolation? Well, I would say yeah, it's not really a coincidence, but it's a very, 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 very deep fact. It's not obvious. It's not very obvious that you obtain the same figure, the same result as in the chapter before. Maybe the best thing to understand why we get this is to think of that system as being a problem of vibration isolation, where you have a spring and a dashpot damper that connects the bearing, center of the bearing, to that rigid block of mass. That rigid block of mass represents your rotating imbalance. So M0 or M0 is equal to M here, and M in our chapter before, when we studied the active vibration isolation for mass force excitation, that M there is then equal to 0. Also, why not then corresponds to E. So if you look at all these correspondences, then you see at least that these problems must be somehow related, but it's really, I would say it's not that you don't have to do these computations we did on the last slide, because it's so obvious that you have to get this figure here. Yeah? So what can we now see and learn from these asymptotics? So from point S, we know that for a low-speed rotor, Rs is equal to E, while R sub W is equal to 0. For the high-speed rotor, it's just the opposite case. Rs is equal to 0, R sub Y is equal to E. Now, what is Rs equal to 0? Rs equal to 0 means that point S is close, asymptotically in, not only close, but in the origin of that coordinate system. And this effect for high-speed rotors is called the self-centering effect. So a Jeffcott rotor with this imbalance here, under high-speed operation, leads to a self-centered rotor in the sense that the center of gravity moves to the theoretical center, to that ideal line that connects the two centers of the bearings to the center of my inertia system. Yeah? So this is very important, and this is what we have to retain as a summary. Let's look again at the asymptotics here. So for low-speed rotors, Rs is equal to or close to E. That would be the static case, and R sub W is then equal to 0. And for the high-speed case, R sub W moves then to E, and Rs is then equal to or close to 0. So both points changed their role, whether you look at the left end of that figure or on the right end, I would say, or on the asymptotic for eta tending to infinity. And then point W and point S just interchange their role in the sense of the position in the inertia system, in the coordinate system. That's very important to retain, and that result, together with the result on the resonance, is summarized in the two theorems of de Laval for stationary operation. The Jeffcott rotor in German and also in the French literature is therefore also called the de Laval, or just simply the Laval rotor. The first result is that there is a resonance at or close to the critical speed, which is the natural frequency of the system. So omega k squared is equal to c divided by m. And finally, so damping is always assumed to be small. Finally, there is the self-centering effect that takes place for very large rotational speed for high-speed rotors. So basically, that's all I would like to show you for the stationary state. We have characterized that stationary state, independence on the rotational speed of the rotor, which is assumed in the stationary state to be constant. So we have characterized the positions of point W and S and their relative position to each other and to the origin of our coordinate system as a function of the rotational speed. Now the question is about the existence of these stationary states. So let's study the existence of these stationary states. The starting point is the third equation we had. This was the third equation. It's the balance of angular momentum. In that balance of angular momentum, we try to derive a necessary condition for stationary operation. That necessary condition is obtained by setting the angular acceleration to 0. This is a necessary condition for stationary operation. And then we plug in the particular solutions for the displacements of point W and for the velocities of point W. So with these particular solutions, and after division then, as you can see, all these particular solutions, they contain the term V. And if we divide the whole equation by V, we divide by E, because E is present in the two terms. So we shift everything to the right-hand side. And we divide also by M. You will ask, why should I divide that equation by M? There is no M present in that equation, because you want to introduce standard parameters. Keep in mind that you then get C divided by M and D divided by M, and you are able then to introduce standard parameters. We shift that equation to standard form. So after division by the magnification factor, by the eccentricity, and by the mass M, we move that equation into standard form, or transform that equation into standard form. You can see we have then omega k squared times the cosine, which sits there, minus 2d omega k omega, which comes from the division of d by m, multiplied with the sine function, which sits here, so y dot, particular solution, and with the negative sign, and we multiply the whole by the sine omega t, and on the next line you find this term, the second term here of our original equation of just the balance of angular momentum without the acceleration term. So you will find here omega squared instead of c divided by m now, and then it's the sine function of omega t and epsilon, minus epsilon here, and you will find plus 2d omega k times omega, which represents then d divided by m, and for the vertical velocity we inserted v omega cosine omega t minus epsilon. I'm sorry, the d divided by m is just 2d omega k, and here also 2d omega k, and the omega stems here from taking the time derivative of the particular solutions. Okay, that's not the end of that line. That should remind you the product of a cosine omega t minus epsilon and a sine omega t, and here sine omega t minus epsilon and the cosine omega t. That should remind you classical addition theorems of trigonometric function. Namely, you then obtain a sine omega t minus epsilon minus omega t and a cosine omega t minus epsilon minus omega t. So the omega t always cancels, and you get just the cosine epsilon and the sine epsilon. So after applying the addition theorems on the cosine and sine, so on these trigonometric functions, you end up with omega k squared sine of epsilon minus 2d omega k times omega cosine of epsilon. That's good. That's a very short representation. And now the question is, what should we do with that representation? Well, the idea is at the very end we will shift the denominator of the right-hand side on the left-hand side. Why? Because everything you can see on the left-hand side depends on the system parameters. We will get a balance then of two torques. The left-hand side, which must be a torque if you multiply by V, E, and M, because it's equal to a torque. So if we did not do any error, it must also be a physical quantity that represents a torque, will be denoted by the system torque. The right-hand side will be the driving torque. Now there is equality between the system torque and the driving torque. And this will be the condition, the necessary condition for stationary operation, the balance between the system torque and the driving torque. What happens if there is more driving torque than system torque in that system? Well, if there is more input than the system can use, then what will happen? There will happen an angular acceleration, a positive angular acceleration. By that positive angular acceleration, of course, the rotational speed will increase, so there is no stationary operation until that increase in rotational speed lead to an increase of the system torque and then balances again the driving torque. On the other side, if you need on the left-hand side more system torque than you have as a driving torque, then you get a negative angular acceleration, and that negative angular acceleration leads to a reduction of the rotational speed of your system. So again, there wouldn't be any stationary operation. So this equality here expresses the fact that there is a balance of so-called system torque and a driving torque. And that equation for the system torque, for the driving torque, we just have to assume some characteristic curves which come from the driving mechanism, for example, an engine or whatsoever. But that system torque, I would like to derive a nice expression for that system torque, nice but still complicated expression, I'm sorry for that, as a function of omega, and we will draw these two characteristic curves, and their intersection mark the state of balance and mark a possible stationary state. A necessary condition, not a sufficient condition. We will discuss sufficiency issues later on. Okay, so what could we do with that equation here? Well, we can introduce expressions for sine epsilon and cosine epsilon, or by dividing the whole equation by the cosine epsilon, we need an expression for the tangent of epsilon, which is just the expression for the phase shift, and an expression for the cosine of epsilon, and that is the expression we saw before. So first of all, let's divide by cosine epsilon, or let's take omega k squared cosine of epsilon to get rid here of that whole term and to represent it by the tangent of epsilon minus 2d eta. If you divide that expression here by omega k squared, you get omega divided by omega k, and this is equal to the frequency ratio eta. And then on the right-hand side, you will find, of course, in the denominator the additional factor omega k squared cosine of epsilon. We represent now, or we replace tangent epsilon by the famous expression for the phase shift, so by 2d eta divided by 1 minus eta squared. You can see I just introduced that term here, minus 2d eta, and on the right-hand side everything is unchanged. Well, we can collect these two terms then by multiplying the second term by the ratio 1 minus eta squared divided by 1 minus eta squared. And then if you have to multiply the 2d eta by 1 minus eta squared, the 2d eta term goes away and we have just 2d eta in the third power divided by 1 minus eta squared. Now we have to introduce the cosine of epsilon. The cosine of epsilon was 1 minus eta squared divided by e eta squared multiplied with v. We introduced that quantity here and we move the whole expression to the left-hand side. That's good, because then we get the cosine of epsilon in the numerator. That is, we get a 1 minus epsilon squared in the numerator, so the term appears in the numerator as well as in the denominator, and so the denominator will go away, we'll cancel with that term. And the e times eta squared moves in the again in the numerator, and so that we get a 2d m omega k squared eta v squared here in that expression. You will wonder perhaps, where is the e? Well, but look, there's another e here, the eccentricity. And if you replace the cosine epsilon by that expression, then you see that also that e here will cancel. So at the very end, we get a short equation 2d m omega k squared eta v squared. That equation will not be as short as represented here. It's nice, but we have to insert the result for the magnification factor v here. Yeah? And for just drawing, of course, this diagram you can use, for example, MATLAB, and you can use that expression in this form. So what you do is you change eta, or the rotational speed omega, keeping omega k to a certain constant, and then you can draw that system characteristic. So you fix all these constants here, and then you can draw this curve. It will look as follows. So this is the equality we have to obtain, the balance we have to obtain. On the left-hand side, you can see the system characteristic curve. On the right-hand side, you can see the driving characteristic curve. And this would be a typical example here. If you remember the asymptotics of v, we will start at 0 here, then we will go up close to resonance, and then we will move slowly but surely in the direction of infinity here with the v squared. On the other hand, so this is the system characteristic curve. On the other hand, we have these driving characteristic curves, and as I said at the very beginning in these assumptions, these should be falling lines, not always linear lines, but falling characteristic curves. They are falling with omega because usually for each of these curves, you see there are several ones, you keep the same amount of power. So if you keep the same amount of power, you have the product of the torque times omega. So then you have to reduce the torque if you increase omega here, the rotational speed of your rotor. Yeah? What can be seen from this figure now? As I said, if we want to have a balance, or for the stationary operation, for the necessary condition, we have to observe the crossing points. And therefore I used one of these characteristic curves, these here, and I observed that for that characteristic curve, so driving characteristic, I find 3 crossing points with the system characteristic curve. So naively speaking, I could say there are 3 possibilities for stationary operation. As this is only a necessary condition, we can't be sure that there is really stationary operation possible for these 3 points. So the question is, if I follow that line here as my driving characteristic curve, and this is my system characteristic curve, would there be a possibility to have 3 stationary states or not? Well, this was a second necessary condition, a sufficient condition. This is not a word Beispiel, but example. For that example here would be a sufficient condition would be the operational point must be stable and it must be reachable. And I will explain in the next few lines what means stability and reachability. First of all, let's assume that the operation starts at rest. So your rotor system is at rest. The velocity, rotational velocity is 0. And suddenly you switch on that engine blob and the driving torque is there. As the driving torque is now much larger than the system characteristic torque, you create a very huge angular acceleration, and as a result of that large angular acceleration, your rotor starts to increase its rotational velocity from 0 going up. And you see that translates into going up that system characteristic curve. So on that omega line for the rotational speed, we move to the right and your system characteristic curve increases until you reach that balance point. And then you are in a candidate for a stationary state. That is, there's suddenly a balance between the system characteristic curve, the driving characteristic curve. So the torque your engine provides is just enough that your system torque is happy and says, well, that's all I need. And I will keep that stationary state. However, there might be small perturbations, right? There might be small perturbations of the engine, so of the torque provided by the engine, or there might be small perturbations regarding some of these system parameters, think of damping and so on, which could be related to aerodynamic effects and so on and so on. So there could be some small perturbations. These small perturbations lead to small perturbations of the rotational speed. So what happens if you reach that point? You feel a little bit happy because you reach a candidate for stationary operation, but unfortunately, due to practical evidences, your rotational speed changes a little bit. What could happen? Well, either it's a little bit lower than that crossing point, which is denoted by omega 1. So either we are a little bit lower than omega 1 or we are a little bit higher than omega 1. What happens if we are a little bit lower than omega 1? If we are a little bit lower than omega 1, then our driving torque is still larger than the system torque. So we will create, again, an angular acceleration, a positive angular acceleration, and omega goes up again. That's good because we move back to that candidate stationary state, and that's what is called stability. We have small perturbations from that stationary state, but due to the fact that then the driving characteristic curve or driving torque is larger than the system torque, we move back, we have a positive angular acceleration, and we move back into that stationary state. What happens on the opposite end? So if due to some external circumstances we cannot control, we have a larger value for omega, so we have a larger rotational speed, some perturbations that lead to a larger rotational speed than that omega 1. Then the system characteristic curve is larger, or the system torque is larger than the driving torque. The system needs more than your engine provides, which leads to negative values of the angular acceleration in order to compensate for this. And the negative angular acceleration leads to a reduction of the angular velocity, and thus the angular velocity is decreased again until you reach that balanced state. Yeah? So that omega 1 is stable. And as this omega 1 is stable, we are not able to move away from that stationary state. So until now, the answer would be there's just one stationary state, it's omega 1, and that stationary state is stable. However, we see that there are two more candidates. And now as an engineer, you would ask, well, but isn't it possible to reach also the other two states? And I personally would rather like to approach the third one, the third state. Why? Because the first one is quite close to resonance, right? And I don't want to get stuck into that resonance. I would like to go beyond the critical speed, because I know then there is this nice self-centering effect we learned before. And the center of gravity moves into the origin of that coordinate system, and the motion becomes quite calm, quite nice. And we have all these nice properties. So we have a high-speed rotor, and of course we know that's also very efficient from an energy consumption point of view. So I would like to move to that point. But is that possible? The answer is no, if you just consider that dashed line. But if you are able, if your engine is able to provide a little bit more power than just that single line, so just for a short amount of time, you are able to move to another curve. So what could you do? You could, until you reach that point here, you can increase, so press the power switch, special power switch of your engine, and you increase a little bit the power, and therefore you increase the characteristic, you move to another characteristic curve of your input torque your engine provides. So in this case, your driving torque is again larger than the system torque. That leads to an angular acceleration. That positive angular acceleration leads to an increase of the rotational speed, and you would increase and you would reach finally that stationary state. And I won't discuss whether that stationary state is positive or not, what I will do as stable or not. What I will do is, when I'm here, I switch off that additional power and I move back to my dashed line. And then I fall back to that balance here between that my old driving torque and my system characteristic torque. And now the question is whether that state here is stable or not. So what we learn is we need an additional driving characteristic curve in order to get rid of that situation, or to get out of that very dangerous situation where we get stuck close to resonance. Now we are here. So what happens when we are there in case we have some small perturbations of the rotational speed? First, if we have a reduction of the rotational speed, so unfortunately we have a little bit less rotational speed than we need for that stationary state, what happens? The driving torque is again larger than the system characteristic curve, so we get a positive angular acceleration, so the rotational speed increases and we go back to that point. And on the opposite end, the same, but with opposite sign, holds. The system characteristic torque is larger than the driving characteristic curve or torque, and this leads to a negative angular acceleration, and that negative angular acceleration tries to reduce the rotational speed, and we move again back to that point omega 3. Now let's assume that we move, also that we get stuck here, we move, switch on our power button, we move to that characteristic curve, and once we are here, over that second candidate for a stationary state, we switch again off the additional power and we drop immediately down to that point. Will this point be stable or not? that can be immediately seen if you look at the position of these two curves, the driving characteristic and the system characteristic. Now you can see you have the opposite behavior. For values of omega larger than omega 2, the driving characteristic curve is larger than the system characteristic curves, which means that we have a positive angular acceleration. That means that your rotational velocity increases more and more again until you reach omega 3. And in the opposite direction, the same holds, but with opposite signs. So you decrease omega, unfortunately, for some perturbations, and then the driving characteristic is lower than the system characteristic torque. That means you have a further decrease of the rotational speed, and you move again through the resonance, very dangerous, and you get again stuck at omega 1. So omega 2 is not stable. So let me summarize what you learned about the stability of these stationary states. Omega 1 is a subcritical stationary state, subcritical because it's below the resonance, below omega equal omega k. It's stable and it's directly reachable from this driving characteristic curve. Omega 2 is supercritical. Here, it's beyond resonance. It's unstable. It's only reachable with an additional driving torque or with some additional power provided to the system. And finally, omega 3 is also supercritical. It's, I would say, the preferred state for that system. It's stable and it's reachable also with some additional driving torque. Well, and that's all I would like to show you, I wanted to show you on the classical Jeffcott rotor. So basically what you have seen is, after stating all these assumptions, you have seen the equations of motion. You have seen that even if these equations of motion are nonlinear and coupled, you are able to solve them analytically. You are able to derive nice results for the stationary state of such a system, and you are able to derive some nice geometric properties, giving you some special insight into the dynamic behavior of this rotor dynamic system, of these bending vibrations. And finally, we discussed the existence of these stationary states, and even there, that stationary solution helps you in order to derive nice equations and a nice discussion on the existence of these stationary states. And this is the end of this lecture, a very, very long video, I know, on the classical Jeffcott rotor. As I said, in the next 3 videos, I will discuss, a little bit shorter videos, I will discuss special effects of this Jeffcott rotor. Thank you very much for your attention, and I look forward to see you again in the next videos on the special effects of the Jeffcott rotor.